Hey everyone, working out of your textbook today. I am on page M2-23. Again, I'm on page M2-23. Hey, so the goal is really to start learning about polynomial division and really applying long division in order to do that. So I'm starting on this page because we're just going to warm up with some pretty easy situations here. I think an easier way to represent 9x divided by 3x is to write it like this. We know we're doing 9x divided by 3x. And then we can break down these pieces. The coefficients, if we divide those, 9 divided by 3 is just 3. And we know that anything divided by itself essentially cancels it out. So this will go in. So 9x divided by 3x, we really just get 3. We can apply the same thing here for 4x squared divided by 2x. So I'll rewrite this as 4x times x divided by 2x. So again, we're doing 4 divided by 2 for 2. And then I just rewrote x squared as x times x. So then we can just see right here, x divided by x, these two things will cancel out. And on the top here, on the numerator, we're just left with 1x. So 4x squared divided by 2x gives us just 2x. This last one, we can apply the same reasoning if we really want to. We can go with x times x times x, because we know that'll give us x cubed. And then we're just dividing by 1x. If you start to look at what gets canceled out here, x divided by x, I still have 2 x's on the top. Another way to write x times x is x squared, not 2x. Okay, so that's really going to be the idea moving forward. And then we'll answer this question real quick. You know how to divide integers using the long division algorithm. How can you use a similar algorithm to divide polynomials? So we're not 100% going to get into this, but I just want to revisit long division because that's something that you haven't done probably since like elementary school. So let's do this. 78 divided by 3. So it's an easy enough problem to do in your heads, but whenever we get to polynomials, this stuff gets like not so easy. So we're going to rewrite this, and instead of like this, we're going to use again long division. So what that looks like is 78 goes inside of this box, and what you're dividing by goes outside of the box. And then you really break down each little piece in here. So we're not looking at how much 3 goes into 78. We're just going to look at how many times does 3 go into 7. Well, that goes in there 2 times. 3 can fit into 7 2 times. And then you multiply 2 times 3 to give you 6. And then we subtract. 7 minus 6 is 1. Drop down the 8. Now, 3 goes into 18 6 times. And then we'll do this one more time. 6 times 3 is 18. 18 minus 18 is 0. So we have a remainder of 0. What that means is 3 goes into 78 exactly 26 times. So we can try one more like that. It's not too time consuming or anything. Let's do 67 divided by 5. So the same idea. How many times does 5 just go into this 6 here, just this first digit? 5 goes into 6 one time. 1 times 5 is 5. After we multiply, we subtract. 6 minus 5 is 1. We'll drop down our 7. Now we have this situation. How many times does 5 go into 17? 5 goes into 17 3 times. 3 times 5 is 15. We'll subtract, and 17 minus 15 is 2. So this time we do have a remainder. The remainder is 2. Or another way of saying that, 5 goes into 67 13 times, but we still have 2 numbers not accounted for. 5 goes into 65 exactly 13 times, but then we still have 66 and 67. We have a remainder of 2. Okay, that's something to look forward to later in the course. Let's flip the page here and go to M2-24. and this is the title of the video, right? The x minus r factor. So we've analyzed graphs before to determine the type and location of zeros. How can you determine the factors of a polynomial given its algebraic representation and one of its factors? So if we were to analyze the graph of this function, we can describe some of the key characteristics. So we know a couple things about this. We know that we have negative end behavior in this direction, positive end behavior in this direction. We know that we have one real solution. We have one real solution, which is occurring right there. That's the only spot that we actually cross the x-axis or intersect the x-axis. We know that we have a cubic function. We know we have a cubic function because, hey, when we look up here, the largest exponent is 3. And just another way to say that, of course, is cubed. So if we have a cubic function, we have a function to the third degree, and we only have one real solution, that would mean we have two imaginary solutions. I'm actually answering this question already, but that's okay. We have two imaginary solutions, and then we have a y-intercept. We have a y-intercept at, so the location of that y-intercept, it's happening somewhere around right here, and we can actually get that from the function itself, 72. So at 0, 72, at that point, we have a y-intercept. So again, describe the number and types of zeros of h of x. Well, we know we have 3 altogether. One of those solutions is real, which means 2 of our solutions are imaginary. Okay, the factor theorem states that a polynomial function, p of x, just some polynomial with x as the variable, has x minus r as a factor if and only if the value of the function at r is 0. Or essentially, p as a function of whatever that value is 0. So whenever you plug in this value into your function, the function spits out a 0. And that's why we so commonly call solutions zeros. So anyways, let's move on to the next page. What would that be? M2-25. So we can use the factor theorem to show that a linear expression is a factor of a polynomial. So consider the graph of the polynomial function that we just looked at in question 1. The graph appears to have a 0 at -8, 0. So we can verify one more time looking at the graph. We see right here that we have a solution at -8. Since we have a 0 at -8, the factor that could produce that 0 is x plus 8. Because remember, whenever we have factors, we get those factors. We set the factors equal to 0 and then solve. So x equals -8. So if this was the factor, right, this is our solution. So another way to check that is what they're doing here. This is what the factor theorem was saying before. If this is a 0, well, when we plug in -8 into the function, that's exactly what they're doing here. The function will spit out a 0. If it does this, you know that x plus 8 is a factor. If I plug in the solution of this factor into the function, and the function spits out a 0, it's guaranteed that is definitely a factor. And again, they're just going through the work here. It's like they plugged in -8 here, and then cubed it to get -512. Plugged in -8 here, -8 here. Added, subtracted all those terms, and they got 0. So that's why it is a factor. For question 2, consider that this function, d of x equals x plus 8, and d of x times something some other function equals h of x. What do you know about the function q of x? So kind of a confusing question if you're not really familiar with the concept. So what this means is, let's just make it a little bit easier. Suppose that d of x equals 5 and h of x equals 20. So if we replace d of x with 5, h of x with 20, then what would we know about the function q of x? So let's try. If d of x was 5 times this function, whatever it is, equals 20. What do you know about q of x in this case? Well, that's easy. We've done this before. We just divide by 5 on either side of the equation, and we would know that q of x equals, 4. So this is really the idea behind polynomial long division. So what do we know about the function q of x? We know that x plus 8 multiplied by, x plus 8 multiplied by, remember they said d of x is equal to x plus 8, so I'm just using some substitution here. We know that d of x, or x plus 8, multiplied by whatever q of x is, whatever that function is, equals, now they gave us the function for h of x up here, this x cubed plus 12x squared. So we know x plus 8 multiplied by whatever this is equals, I'll just write it on a new line, x cubed plus 12x squared plus 41x plus finally 72. We know that x plus 8 multiplied by whatever this function is equals h of x, or I just gave you the actual terms and values for h of x. Okay, so can you write the algebraic representation for q of x? So remember going back up here where I divided by 5, or I divided by whatever d of x was. So here's what it'll look like. We know that, once again, we know that this is true. D of x times q of x equals h of x. So what we'll do is apply some algebra, like I did up here where I divided by 5, and just, instead of using the kind of made up scenario that I gave here, we'll just divide by d of x. D of x divided by d of x, anything divided by itself gets canceled out. I'll do the same thing on the other side of the equation because, algebra. So q of x equals h of x divided by d of x. Q of x equals h of x divided by d of x. Or q of x equals x cubed plus 12x squared plus 41x plus 72 divided by x plus 8. All right, so this is really what we're going to be focusing on this week in class. How do we divide all of this stuff divided by a linear factor like x plus 8? And again, the process is going to be long division. So make sure you kind of understand and remember these steps where you break down each little digit, or in polynomial long division, it's going to be each term. And then how many times does it go in? Multiply, subtract. So we'll go through the process later this week. This is just giving you an intro of what to expect. So anyways, thanks for watching. See y'all in class. Bye-bye.